Good morning, everyone. In the last class, we started discussion about the Gaussian distributions. The reason why we started discussion about this Gaussian distributions, which are otherwise also known as the normal distribution, is that when your output is a result of addition of multiple random variables, your final random variable, even if you call it, if that is a result of addition of multiple random variables, then that irrespective of what the distribution of individual random variables is, your final distribution will be Gaussian. It is for this reason this is widely studied, widely used, right? In addition to the reasons of tractability of it and easy of convenience of analysis of it. In practice, you could observe Gaussian distributions in quite a few scenarios. I'm sure you all know the central limit theorem that tells you about this, how addition of multiple random variables would with any distribution would eventually result in a Gaussian distribution, right? So yesterday in the class, we discussed about the Gaussian distribution, and I have written this formula. So why is this variable or the scaling factor is introduced into this Gaussian distribution? Any idea? You see there a scaling factor of 1 over square root of 2 pi into sigma. Why is that there? Have you ever thought
Total integration from minus infinite to plus infinite of 1.
That's right. To normalize your distribution such that when you integrate it from minus infinity to plus infinity, you will get 1. Why is that important?
Sir, because this function is summation of all probabilities, which is equal to 1 ultimately.
Correct. What is that function? We call it as
PDF, probability density function.
Because you are eventually going to model your likelihood functions with this Gaussian distribution, and we are dealing with all the probabilities, and this turns out to be a probability density function. Once you do this, it is as simple as the way we converted histogram to a probability density function while we are doing histogram equalization. Same logic holds here. Hope everybody is clear with that. Okay. Second question before I go with new things is, we have written yesterday expressions for this mean and standard deviation. Are they true for only Gaussian distribution or any distribution for that matter? I give you some other distribution of probability distribution, not necessarily a Gaussian distribution. I can have many types of distributions, like even some skewed kind of distribution could be there. Quite a few distributions are there, or it could be a non-parametric distribution, which you may not say. The question is, are the definitions or formulas we have worked out for mu and variance, are they true, or are they valid only for a Gaussian distribution, or are they valid for any distribution in general?
So these formulas are valid for all distributions.
Correct. Very good. So this has nothing specific for any special, any specific thing for Gaussian. As one of you had earlier tried of giving mean and variance in different ways. One of you have told that you look for a peak. Yes, that's in fact true. It is true for a pure Gaussian distribution. If it is not a Gaussian distribution, any given distribution, these mu and sigma square formulas holds good. Okay, if you recollect, this is how for any histogram, not necessarily of Gaussian distribution, we calculated mean and variance in this manner only. Essentially, you are looking at how many proportion of values are having that particular x. You are multiplying with that x value, and you are doing so on and so forth. Anyway, normalization is taken care by that 1 over root 2 pi times sigma. So eventually you will be going to get mean value. For variance, you are subtracting the mean value and the and then expected value of that x minus mu square would eventually give you sigma square, irrespective of what the distribution is. I hope these 2 points are clear to one and all. let's now move on from 1D distribution to two-dimensional Gaussian distribution. Or maybe by the way, this distribution is also referred to as univariate Gaussian function. Uni means one. I'm sure most of you would have been already knowing that. So this is also referred to as univariate Gaussian distribution. Okay. So what I will do now is let's write an expression for a, now we call it as a multivariate. It means all it says is it can vary in multiple directions. That means it's a multi-dimensional Gaussian distribution. So that's what we will do in today's class. For reference, let's first write again the univariate Gaussian function that we have worked out and analyzed yesterday. How is that written? Let's write it as a probability density function itself. Please work out along with me. Is equal to 1 over square root of 2 pi into sigma. And there is an exponential of minus of x minus mu whole square over 2 sigma square. Correct? This was the univariate Gaussian function. Now, let's write the expression for multivariate, means any dimension. Multivariate Gaussian, you can call it Gaussian function or Gaussian distribution, whichever you may call it. That's what we are going to write now. Okay, so let's move on now to from probability of x to probability of x bar. Will the final value of x bar, probability of x bar, be a vector or a scalar?
It's scalar only, sir. Probability is always
Correct.
scalar only.
See, for example, if you want me to show a two-dimensional graph like this, where it's a 2D Gaussian, you have two, x bar is x1 and x2 you are giving. The value at that is a scalar. This has to be very clear in your mind. Okay. So then let me write how this is defined. Okay. Pay attention to the word I am using. This is how we are defining a multivariate Gaussian distribution. Right. So for x1, first let us write this multiplication factor. Let us also say that x bar is, as usual, an L-dimensional feature vector for us. So what do you think square root of 2 pi? So you have that Gaussians in L-dimensional space. So what do you think you would get there? Square root of root 2 pi whole power? What do you think you will get there? Any guess there?
Covariance.
No, I'm just saying covariance will come. Sigma is there in covariance. I'm just talking about a simple scalar multiplication factor of 1 over square root of 2 pi. Now, when I move from one dimensional to L dimensional, what do I get there? Root 2 pi power
L by
power L. Is it not? Just I'm multiplying Gaussians. You could think of like that. Now, instead of sigma, now, instead of a single variance value, I will be getting here multiple variances are there. It can vary L-dimensional space. It can vary in the direction of x1, x2, x3, x4, and so on. But should that resulting value be scalar or a vector of whatever I'm going to write in this denominator? See, I'm telling you all these things because otherwise there will not be any intuition for multivariate Gaussian distribution that you are going to see. You should have at least some intuition to what it means and why it is so. Okay, what do you expect there? Should it be, all I am asking is whatever you are going to put in the denominator there, instead of a variance, you will put something related to covariance. All I am asking you is, should that whatever quantity I put there, should that give you a scalar or a vector? Covariance matrix, I would call it as this summation signal. Okay, that's my covariance matrix. And I take the determinant of it and then square root of it, where this is a covariance matrix. Notice here, as I am taking a determinant here, will that be a scalar or a vector now?
Scalar.
That's all. You are taking a determinant of it. Okay. Covariance matrix. What would be the dimensions of it?
L cross L.
Right. Okay. As far as the dimensionality of this multiplication factor is concerned, now let's try to write something inside this. Exponential of minus, pay your full attention here, x minus mu. Finally, the value inside exponential, should that be a scalar or a vector? The whole term inside, after doing that x minus mu whole square by sigma square, should that be a scalar or a vector? In the interest of time, I write expression and then I'll ask you. So minus 1 by 2 is anyway I'm writing there. I am writing here x bar minus mu bar whole transpose into covariance matrix inverse into x bar minus mu bar. Okay, this is what I have inside the exponential. Now at least you tell me what is the expression inside my exponential. Is it a scalar or a vector? What is my x bar? x1, x2 up to, it's an L dimensional one. So what should be the last value?
XL.
Right. And then mu bar. So x bar is of L cross 1. Mu bar will be what? What would be the dimensionality of mu bar? That's the mean values in L dimensional space. So mu bar is a vector of size
L cross 1 only, sir.
mu1, mu2, so on, mu L. Okay. Are they enough for me? Right. Now let me come here. What is the dimensionality of that matrix? X
1
bar
by L.
minus mu bar whole transpose is 1 cross L. What about inverse of this covariance matrix? What about that size of that matrix?
L cross L only, sir.
L cross L. What about this?
L cross 1.
What about this multiplication?
L cross 1.
What about this multiplication?
1 cross 1.
Right. 1. So is the argument inside exponential scalar or vector?
Scalar.
Scalar. Good. Now you see here. That should be ideally that now you see how we have written x minus mu whole square in a vector form that is equivalent to x bar minus mu bar whole transpose into x bar minus mu bar. Now in the denominator you have sigma square. So it is equivalent to, when you write it there, bring it to the numerator, it is an inverse. That's where this has come here. And finally, this is having a single value. So it is in this particular order that you are writing things. So did you get some intuition now? Is it clear? And why this expression for multivariate Gaussian distribution is written in this manner? Are any questions or doubts here? This we will use now left and right throughout this course. And of course, in many places, you will come across multivariate Gaussian distribution. So a sound understanding of the multivariate Gaussian distribution function is indeed essential. So is this clear or not? Now what we will do now is just to get a little bit better understanding of how this looks like and all, let's consider a special case of two-dimensional Gaussian vector. So the special case I'm going to consider now is L equal to 2. Now, let me write these expressions for L equal to 2 then. Okay, so how could I write then my probability of, hope you also please try to write along with me or competing with me, writing it a little bit faster. So essentially, this is probability of a function of both x1 and x2. Since I am writing it as a function, I could write it in the same row kind of stuff. Ideally, otherwise, there are other notations in which I could write 1 over square root of root 2 pi whole square there, L equal to 2. So I have 1 over 2 pi. Then I have the covariance matrix, determinant of it. So sometimes people forget that this is a determinant. If they forget it, whole thing gets screwed up, because that will not be anymore. If you are taking just a square root of that matrix, it's a matrix, but eventually it's a scalar. So pay attention to that. Then exponential of, right, minus 1 by 2, easy to write. So I'll still keep that minus 1 by 2 here. And here I have x bar minus mu bar whole transpose. What would be the size here? 1 cross 2. So I could write here x1 minus mu 1 and x2 minus mu 2 in this way. Hope you all agree with that. Then inverse of that, I will expand that a little later. Then all I have is x bar minus mu bar 2 cross 1. So I would write it like x1 minus mu 1 x2 minus mu 2. This whole exponential. Okay, hope you are fine with that. Mu bar, essentially what I did is mu bar has been written as there mu1 and mu2. How do I get that? It's nothing but the expected value of x1 and expected value of x2. This we have done now, right? So that's what your mu bar in that is there. So for the individual distribution of x1, if you know the expected values, you could write that. Now, next question is, how can you write this matrix in terms of expected values? Covariance matrix is expected value of what? In a one-dimensional case, how did I write? So that it will become clear to you. In a 1D case, so sigma square is expected value of, you have written it in the previous class.
X minus mu whole square.
Right. Now, tell me this, what is the dimensionality of this covariance matrix?
L cross L.
L cross
So
L.
2 cross 2.
Right. Now you tell me, how do you write that x minus mu whole square inside?
X minus
x1
mu
minus mu1.
Okay. Then what? Should I write a column vector first or a row vector first?
multiplied by transpose.
Correct. Correct. Very good. So here what will come? X2 minus mu2. This vector multiplied with x1 minus mu1, x2 minus mu2. Good. This expected value would give you the covariance matrix. See, if you do not follow these steps and if you don't get this intuition, everything looks like why it is defined that way. There will not be any clue or clarity. So this has to be very clear to you. So instead of the x bar, It is now if you write x times x minus x bar minus mu bar multiplied with, okay, x bar minus mu bar whole transpose, right? This is 2 cross 1, this is 1 cross 2, you will get 2 cross 2 there, means that's how you are defining the terms there. So x1 minus x bar minus mu bar is nothing but whatever I have written here, x1 minus mu1, x2 minus mu2, the first column vector. It is followed by the row transpose of it, which is nothing but x1 minus mu1 and x2 minus mu2. Now, can you further simplify this now? This is equivalent to expected value of, you tell me now the matrix there. First element of that matrix.
x1 minus mu1 square.
Very good. Second element in the same row.
x1 minus mu1 into x2 minus mu2.
Good. Second row, first column.
x2 minus mu2 into x1 minus mu1.
Same one, right?
Yes.
Good. What is the last one here?
x2 minus mu2 square whole square.
Right. So all we did is just a matrix multiplication is what all we did it. So this value, you typically, you are now going to compute expected value of x1 minus mu1 square, expected value of x1 minus mu1 into x2 minus mu2, and so on and so forth. So if you want, of course, I could write this as expected value of x1 minus mu1 square, expected value of x1 minus mu1 into x2 minus mu2, expected value of same thing here, and expected value of x2 minus mu2 whole square. This is my, what is this? This is my covariance matrix. This is what is my covariance matrix. I know how to compute expected value of a given thing already, I know, right? How do I compute it? Integral over, we have done it, right? X into that p of x minus infinity to plus infinity dx. So that instead of that x, you have these things for computing the covariance matrix. So sometimes you would simply write it as sigma 1 square, and here sigma 1 2, sigma 1 2, sigma 2 square. Okay, if you are given a distribution, now you should know how to compute this covariance matrix as well. Okay, this is what has been attempted here. Okay, the formula has been given here. This is the covariance matrix, and you sometimes, if these variables x1, if the variables, if x1 and x2 are statistically independent, any idea on what would happen then? If they are statistically independent, can you guess what would happen to some of the elements of this covariance matrix?
Sigma 1 2 becomes
Zero.
0.
Correct. Sigma 1 2 will become 0. This is also very easy to prove. I leave that part to you. So if you understand what it means by statistically independent mathematically, you will be able to say it. Suppose if my probability distribution of x1 comma x2 can be written as When is it statistically independent?
Probability of x1
Hmm.
into probability of x2.
Very good. Then you call it statistically independent. So I have not done it myself, the proof, but I ask you to make an attempt on that, where you already know P of one-dimensional Gaussian distributions. We have already written here. The very first expression that we have written is that. So take probability of x1 there. So x1 minus mu1, okay, and sigma 1 there. And similarly take probability of x2 there, and see how for what values of this both will be equal. If you do that, you should be then will be getting this result of sigma 1 2 equal to 0. Then you could rewrite it, and eventually you will realize that if this is true, P of x1 into P of x2, if you multiply and try to equate it to P of x1 comma x2 that we have written, and equate both, you would realize that sigma 1 2 will be equal to 0. So I want every one of you to work it out. Okay, there is something called as isocurves. Did any of you hear that? Isocurves or isocontours, did you ever hear? This is essentially you have a distribution on which you want to just plot it on x and y. Okay, so you see this Gaussian distribution, two-dimensional Gaussian distribution means for a given x y value, it has a particular value here. If you notice, for a given x1 and x2, it has a particular scalar. Okay, I don't want to plot surface plots when I am doing it on paper. If I don't want to use difference of intensity to show that value also, if that is also what I don't want to do, there is another simple way of representing things which is referred to as isocurves. Very convenient. Does anyone of you have any idea on what they mean? Essentially, you will plot the contours. The contour is that where all the points on that contour have a same value. That's what you refer to as isocontour. Okay, so like say for example, for this so where does this now, what is the exercise that we are going to do now is, let's assume that your mu1 and mu2, your mu1 and mu2 are 0. So you have a zero mean thing. Okay, for a given, this 2D Gaussian distribution is centered at 0 comma 0. What does this mean? This distribution for a given class is centered at 0 comma 0. That's all. Otherwise it will be just translated to some other point. Okay, now look at here. Where should I start? What I will do is I will, let's say, take this part here. Which one? This is nothing but X transpose, right? X transpose inverse of my covariance. So when will they have same value? When my argument inside exponential is the same for those set of, pay attention here, for those set of x1 and x2 values for which the argument which is there inside this exponential is the same, I would, all those points will have a same value. Are you with me? Are you able to follow this point? All I am saying here is, let me again copy this form for you. So all I'm saying now is, these are all the points at which this function has same value. That's what we are referring there. Now I'm further simplifying this. I would make it as mu1 and mu2 are 0. So inside for me, for a two-dimensional case, I have x1, x2, and sigma inverse. What is that value? And again, let me also assume here, what should I assume? Statistically independent. That means sigma 1 2 equal to 0. Then what do I have here? For example, I will have sigma inverse will be equal to 1 by sigma 1 square, 0, 0, 1 by sigma 2 square into x1, x2. This is my argument. I'm not sure
Excuse
if
me,
you are
sir.
all. Hmm? Are you with
Sir,
me or yes?
Sir, we have assumed that mu1 and mu2 are 0, sir.
Correct, correct.
Okay.
For the time being, let me first tell you the purpose. I would like to see how does this, what would be the shape of this isocurve. Okay, that's my first objective. What will be the effect of mu1 and mu2? This whole distribution shape will be moved to some other. If it is at 0, 0, it is at that point I have a 2D distribution whose mean along x-axis is 0 and along y-axis is also 0. So it is symmetric about the 0, 0 or whatever you call there. Okay. Then I am also assuming statistically independent. And then I am trying to see what is the shape of this isocurve. Further, I assumed that sigma 1, 2 is also 0. Is that clear?
Yes, sir, it is clear so far.
Okay, good. So now that means now all I want to see is forget about this being a constant. So I could even ignore minus 1 by 2 there. I would like to see which are all the points that have the same value. So what I mean by that is x1, x2, 1 by sigma 1 square, 0, 0, 1 by sigma 2 square into x1 times x2 here. This is equal to c. Okay, if you don't like me dropping minus 1 by 2, you take it and multiply on the other side with minus 2 and call it with new variable c. Okay, now what is the value of your left hand side now? Calculate and tell me what is it a scalar or a vector on the left hand side? It has to be a scalar.
Scalar.
Yeah, what is that value? Tell me.
x1 square by sigma 1 square plus x2 square by sigma 2 square.
Is equal to
See, concept.
very good, very good. What is it? What is the shape of this?
Elliptical.
Ellipse. If sigma 1 and sigma 2 are same, it is going to be
Circle.
circle. So what's the message here? What is the inference that you could draw here? Just can you put it into a statement, a single statement of what I have done for isocurves here? And give me a summary in one statement on what I could draw, or what is the conclusion that I could draw here?
The ellipse will represent the variance of x1 and x2.
Not the variance. No, be careful with the word variance because we use it in a very professional way. Variance is something here. Isocurve, that's what we are already saying that. So try to put it in your own statement here. Refine your statement further. If sigma 1, 2 is 0, then if I consider all those points which have a given value, okay, given value of probability density, I could call it here, then all those points, the locus of all those points will be fill in the blanks. I came from forming a statement to a fill in the blanks. The locus of all points, when I consider a two-dimensional feature vector and statistical independence between the two distributions and zero mean, then the locus of all points that have a constant value is
Ellipse.
ellipse. Very good. Now let me again come back to normal mode and show you some illustrations. The statement I made here, see, I considered here the sigma 1, 2 equal to 0. That means statistically independent. These feature vectors, components or elements of your feature vector are statistically independent. I considered a 2D Gaussian distribution or I could say my feature vector has two components. Then the value is given by this expression. Anyway, this outside multiplication factor is same for all. Here, if I look at it, if this value for all those sets of x1 and x2, for all those sets of x1 and x2 for which this expression has the same value, obviously they will all have the same value there, because exponential of that you are giving for all those combinations. So what we worked out is what would be the locus of all those values, isocontour. So what I did is simply equate that which is inside a constant value. When am I getting a constant value? That gave me an ellipse. So you see now some graphs here. Again, you should have a mathematical vigor. You should be able to deal with things mathematically. Thus, you should possess. At the same time, you should have a very clear intuition, interpretation, and understanding for all the graphs and the results that you get. Okay, that you keep it in mind. We did some mathematical exercise so far. Now let us see what this tells us. Zero mean and zero variance. Zero mean is considered, sigma 1, 2 is made 0. This is my covariance matrix. What does 3 and 3 tell us here? The diagonal being 3 and 3, what does that tell? Your variance in x direction, x1 and x2 are the directions. Hope you could see here x1 here. This is in x1. This is in x2. Now, the variance in this direction is 3. And in this direction is also 3. Now, obviously, if that, then what is plot here on the right hand side in the part B is the isocontours. You would see that at the center 0, and if you take some value of, let's say, 1, 2, 3, 4, 5, and so on and so forth, and if you plot those things here, you would see that you get circles there. And of course, when your sigma 1 square and sigma 2 square are equal, this is the equation of a circle. And obviously, what you get here, the isocontours are circles. You could also observe from the graph that the variance in x direction and the variance in x1 and x2 directions for that Gaussian distribution is varying almost in the same manner. Not almost exactly, just that the view is constrained, because at the end of the day, you have to show on a 2D, a 3D curve. So we make a visualization for that. So that's why another way we resorted to is plotting an isocontour. Another graph here. Okay, again, let's make a similar interpretation. Now I have sigma 1 and sigma 2 different. Sigma 1 square is taken as 15. Sigma 2 square is taken as 13. What does that mean? Along x direction, there is a larger variance around your mean value compared to what you have along x2. That is obvious from here, such that, well, here you could see the variation is larger along, this is your x1 plane. So in this direction, you would see a larger variance in your graph compared to the other one, x2 here. That's only 3 there. Now again, I am plotting here the isocontours. Obviously, they are ellipses. Since you have larger variance along the x1 axis, of course, you will have now the major axis along x1 and minor axis along x2. And this is obviously an ellipse with its major axis along x1. Clear? Can you correlate the covariance matrix to the graph and covariance matrix to the plot to the isocontour? All these 3 steps should be clear. Are you fine with that? Then another one where it is exactly the opposite now. Your sigma 1 square is 3 now and sigma 2 square is 15. Of course, from the equation also you could figure out this is just change of variable x1 to x2 and x2 to x1. Since you are keeping your x1 and x2 same, your graph will now rotate 90 degrees. Right? Mathematically also you could relate that. And of course, then the variance along your x-axis, you just move along your x-axis, you would see that this is less, and along your x2 axis, it is more. This is what would happen. And the another case, which we have not mathematically derived, but easier for you if you know eigenvectors and eigenvalues, from there you could make an interpretation here, but that part I'll leave it to you. But intuitively, let me give you some analysis or insight here. Now what has been done there? This is 15. That means along x-axis, the variance is more, that's 15. Along y-axis, it is 3. So 15, 3 is same as this you have considered. Then there is a sigma 1, 2. The dependence is also there. And that's, let's say it has been taken as sigma 1, 2 is taken as 6 here. So what it will do is, essentially, it will tilt your thing. You will still get an ellipse, but a rotated ellipsis is what you would get there. It's equivalent to rotation. If you make analysis of matrices in terms of eigenvalues and eigenvectors, you would realize that it's equivalent to the earlier matrix multiplied by a rotation matrix there. That rotation will be known by this value of sigma 1, 2. But then all you would get is still ellipses, if provide, but at some angle is what you would be getting. To summarize what we looked in this class is, since the likelihood likelihood functions for each class will be approximated with the Gaussian in many cases, and your feature vector need not necessarily be one-dimensional. Of course, it will not, in most of the cases, it will be many-dimensional, L-dimensional space. We should get a fair understanding of writing that equations in L-dimensional space. So L-dimensional Gaussian functions I have to write. So that's what multivariate Gaussian functions, that preparatory work has been done here. To get a feel of them, we again descended down or came down to a case of two-dimensional Gaussian distribution. Not only that, we have seen for a given value, this is important because later while you compute the decision boundaries, there you would see the value of this versus that class versus this, where it is same, then only you will find out the decision boundaries. So for that reason, you would indeed need to find out these isocontours. For two reasons we are doing it. One, its representation makes it simple to represent it like we did here. The second, later you would realize that when you are trying to find out the decisions, this helps us. For these two reasons, we have also used isocontours. In 2D, we have realized that if your variance in x1 and x2, sigma 1 square and sigma 2 square are same, the isocontours are circular. If they are different, they are elliptical, and the major axis depends on in which x1 or x2 the variance is more. And finally, the other one, if you have non-zero covariance sigma 1, 2 value here, statistically dependent, they are distributions in x1 and x2, then what you are going to get is tilted ellipses. Okay, I'll stop here.